Hello and welcome to another Senior Curriculum Inspiration proudly sponsored by Texas Instruments Australia. The Curriculum Inspiration series is designed to help teachers to develop strategies in the effective use of Texas Instruments calculator and software in the classroom with carefully selected and pedagogically innovative and sound mathematical activities. My name is Peter Flynn and I'll be your presenter for this session. Today we'll be focusing on the activity titled Pythagoras is not real, and I'll be using the Texas Instruments CX-CAS platform. A shout out to Peter Fox, who helped develop or actually develop this particular activity. Today's activity comes from Specialist Mathematics Year 11. All the files for today's activity can be downloaded as shown on the top right of the screen. The components of the activity consist of a student worksheet, a teacher worksheet with helpful notes in blue about the activity and answers in red. As well as that, there's a TI-Nspire or TNS file for students to explore throughout the activity. About the lesson, what students are asked to do in this exploratory activity is to manipulate a point represented by a complex number on the Argand plane, to look at the corresponding value of z squared, which is also plotted on an adjacent Argand plane, and if the real and imaginary components of z are integer quantities, then the real and imaginary components of z squared form the shorter side lengths of a Pythagorean triple. And after getting students or encouraging students to identify a collection of triples, students that are undertaking this activity are then required to prove that this result always works. There is an extension that allows students to also informally explore the polar form of a complex number. At the start of this activity, students are asked to take 4 complex numbers, as you see there, and for each of them, they're asked to calculate z squared by hand with the resulting work shown on the right-hand side there in red. This is an excerpt from the teacher worksheet. And what you can see in part A is that if z is 2 plus I, then z squared is 3 plus 4i, and 3, 4, and 5, if you work out the magnitude, is a Pythagorean triple. Then in the next one, z equals 3 plus 2i, you calculate z squared, and z squared is 5 plus 12i. The magnitude of z squared is 13, and again, you end up with a Pythagorean triple 5, 12, 13, and so on. In part C, it's the one that's not very well known, 20, 21, 29, and in part D, 7, 24, and 25. It's only a small file, and it's quite easy to work with. It consists of 2 pages. The first page is just giving the students a heads up as to what the activity is about, and also how to interact with the activity when they go to page 2 or 1.2. So students are asked to go to 1.2, and what you can see there is that the calculator screen has been split into 2 graph applications. Each graph application contains an Argand plane. On the left-hand side, it's for Z, and on the right-hand side, it's for Z squared. And what you do, it's a dot grid, and what you do is you grab the point Z and you move it around so that it ends up on one of those dots. In other words, it's always the real and imaginary components are always positive integers for the purposes of this exercise. So you encourage students to move Z around the Argand plane on the left-hand side, and what happens on the right-hand side is you get a corresponding update for the complex number, which is represented by Z squared. And what you will always also note is that there is a different scale for the imaginary axis on the right-hand side, because the imaginary component can start to get quite large. And so to be able to see it on the screen, we need a larger scale for the imaginary axis. So that's a point to ensure that students are aware of, that the scale for the right-hand Argand plane as for the z squared values have a much larger magnitude. The activity then goes on to ask students what they note from moving Z around the Argand plane on the left. And so getting students to display Z as 2 plus I, they'll get an automatic update of Z squared being 3 plus 4I, and then you can ask them to determine the magnitude of Z squared, and also to get them to identify the Pythagorean triple that Z squared relates to, where Z equals 2 plus I. And you can see that that's the case for question 3 and question 4, where in each instant, Z in question 3 is 3 plus 2I, and in question 4, Z equals 5 plus 2I. So the term that's being used there is drag. So it's making contact with the point and dragging it to that particular location. As with these activities, we often look at specific cases and then ask students for some sort of generalization. So in general terms, if we let Z equal A plus BI, where B is greater than A is greater than 0, we can ask students to have a bit of free play and ask them to create 3 more imaginary numbers, or and check if Pythagorean triples are produced through Z squared. Of course, answers will vary amongst the class. Some will be multiples of other Pythagorean triples previously generated, so that's good to note. For Pythagorean triples, having the real component greater than the imaginary component means that the arg of Z is less than pi on 4, which means that the arg of Z squared is less than pi, resulting in positive and real imaginary components. What's nice about this activity is that after having a bit of a play and having some sort of understanding of what's happening, we then ask students to undertake a generalization. So if we let Z equal A plus BI, we can show that the real and imaginary components of Z squared will always produce the 2 shorter sides required for a Pythagorean triple. So when Z is A plus BI multiplied by A plus BI gives A squared minus B squared plus 2ABI. So you can isolate the real part of Z squared and the imaginary part of Z squared. And then what you can do is you can take each of those, square them, and then add them together, which is in the next 4 lines of work, and you end up with A squared plus B squared all squared, which is a perfect square, and which shows that the real part of Z squared all squared plus the imaginary part of Z squared all squared is A squared plus B squared all squared. The extension question is very nice. If you have a look at that screenshot there, the slider on page 1.2 can reveal the angle Z makes with the real axis and also the magnitude of Z. And it's quite a clever slider. You click on it once and it reveals the angle. You click on it a second time and it reveals the magnitude. And you click on the slider a third time to reveal both the angle and the magnitude. These measurements are dynamic and they're updated when you move Z around the Argand plane. And you can ask students to look for patterns relating to the angle Z that is made with the real axis and the angle Z squared that is made with the real axis. And you can also do it for the corresponding magnitudes of Z and Z squared. And so what you want the students to be able to glean from this is that the angle that Z squared makes with the real axis is double the angle that Z makes, and the magnitude of Z squared is the square of the magnitude of Z. Well, so here's the TNS file, and as I said, you make contact with the point and then move it along 1 and then up 1, for example, to Z equals 3 plus 2I. You'll notice that when Z moves, Z squared moves, and then this very clever clicker or slider, so you click on it, it shows you that the angle that Z makes with the positive direction of the real axis is 0.588, and for Z squared it's 1.18. So that appears to be double. the magnitude, distance from the origin to the particular complex number. For Z, it's 3.61, and for Z squared, it's 13, and you square 3.61, or you square root 13 in exact form, and you get 13, and there's the two results on the screen at the same time. So that's nice. So you can have that on, and then you can change the location of Z, and you can note there that there's a doubling effect of the angle. Notice also that Z squared has moved over into another quadrant, and also note that when the magnitude of Z is 5, the magnitude of Z is 5 squared, or 25. So I think when we teach complex numbers, often it's in quite a static environment, and this gives us an opportunity to look at complex numbers in an interactive, dynamic environment where students are given the opportunity to note some results, to form some conjectures, and to test them out, with greater formality to come later on in the teaching and learning of complex numbers. So I hope you've gained some useful ideas that can be used in your classroom to inspire your students from this Curriculum Inspirations session. That's all we have time for today, so please visit the Texas Instruments Australia website for more free activity lessons that make students explore, discover, and visualise mathematics through using the Texas Instruments technologies, and for when the next Curriculum Inspiration is scheduled.